So hello, this is WF7I YouTube, and today I'm going to go through aspects of this tri-band receiver that I designed. And I thought I would go ahead and go through the circuit schematic on LTSpice. So I'm basically just using LTSpice here as a CAD program, a way to kind of illustrate the circuit. I'm not actually simulating the circuit this way. But this was a tool that I had installed on my computer, and I'm fairly familiar with how to use it. And it was, for the moment, kind of the easiest way for me to document the circuit and create a schematic. So that's what I'm using. LTSpice is a great tool for doing circuit simulation, and it's free. So if you're not familiar with it, I'd highly suggest getting a copy and downloading it if you want to do any circuit simulation work. So without further ado, I have the circuit broken down into different components on here, so it's a little easier to visualize what's going on. So this first part here, let me just zoom in on it a little bit, is the NE-602 chip. So that's the doubly balanced mixer chip, and that is sort of central to the design. And what I had mentioned before in an earlier video was there is an onboard oscillator on this chip that's commonly used. I've also seen people build their own oscillators in conjunction with the chip, and that's what I chose to do because I was not able to really get consistent results or good results with the internal oscillator on this chip. That remains to be another project that I'm going to want to investigate in the future to see if I can get that to work a little better. But at any rate, so this is sort of where the signal comes in. So you have the antenna port here. This is my RF gain control, a little 5K audio taper pot. And that is to cut down on some distortion that results from strong signals impinging upon this chip. Chip's very sensitive and very prone to, seems to be very prone to kind of an overloading situation, at least the way this is implemented here. So that helps an awful lot to cut that down. And it's also, in this particular circuit, is serving as a volume control. I'll talk about that a little bit more later as far as volume control. And then what I have here is a switch. So I have the switches labeled SW1, 2, and 3, 4. What it is I have a multi-position switch. So it's 4 poles, 3 positions. So 3 positions are 20, 40, and 80 meters. And each pole I've labeled as like switch 1 is 1 pole, switch 2, switch 3, switch 4. Those are the 4 poles. So for the pole number 1 here, it's going into bandpass filters, the BPFs. That helps cut down some of the strong out-of-band signals that are hitting the chip and sort of helps to define what the pass band is of this circuit, of this receiver. Otherwise, it's really pretty much wide open to all RF signals coming in, which is, you know, not really an ideal situation. So what you have there is, again, your bandpass filtering that comes in, and then after that there is a roughly 4-to-1 transformer, and the 4-to-1 transformer helps to convert the impedance from a very high impedance, or I'm sorry, a very low impedance, around 50 ohms of my typical antennas, to a, something approaching closer to the 1500 ohms input impedance, pins 1 and 2 of NE-602. In actual practice, and this is another thing I'm going to need to study further down the road, for some reason using this and many other toroidal cores, I was not able to get even really a 4-to-1 ratio as far as transformation. So 10 to 40 turns should give you about a 4-to-1 voltage transformation, or about a 16-to-1 resistance transformation. And if I just pull it up on my calculator, 16 times 50, that gets you about 800 ohms. I achieved that, I believe, on 40 and 80, but 20 was really tough. I don't think I quite got that. And no matter what I did with cores and windings and various things, I could not get a transformer to really transform more than about a 4-to-1 ratio. I couldn't go 5-to-1, let's say. I don't know why that is. Some people watching this may know why. I think it's just a matter of me doing a little bit more research into maybe balance and things like that to see what they're using. I don't know, but 20 meters for some reason in particular seem to be hard to get that transformation. So anyway, this is roughly a step up in impedance so that we have better transfer of energy from the antenna to the mixer inputs pins 1 and 2 here. Pin 3 is grounded. Pin 4 is the output of the mixer, which is, again, you're mixing the direct conversion way, so your local oscillator is your frequency of interest. So you're beating against the same frequency essentially, and the difference frequency is audio. So that's what's coming out here is audio frequencies. And that's going to go to the LM386 chip. Here, the input from pin 8 is 8 volts. I use a regulator chip to get a relatively stable 8 volts. So I use 12 volt power supply, and I'll get to that in a second. But 8 volts regulated to the 602. Pin 7, I ended up grounding, RF grounding through a 0.01 microfarad capacitor. I felt that might have added a little bit of stability with this implementation, a little bit less noise perhaps. Pin 6 is the input from the oscillator, which is shown elsewhere. And so what happens is I have 3 different oscillators, 20, 40, and 80, and they go through switch 4. And I had to step down the amplitude of the oscillator. That's why I ended up with this huge resistor here. That is not an ideal design by any means. Probably what needed to happen is to sort of adjust the oscillators to provide a lower amplitude. But I really didn't want to play with that too much after I had gotten the oscillators tweaked the way I wanted. So I ended up putting in this resistor here instead. Otherwise, I found, kind of like with a lot of things with this chip, it's very sensitive to generating a lot of noise, out-of-band signals, and things that I don't want. And if you put a really, really strong local oscillator, you know, in the order of several volts peak to peak or whatever coming in here, it seemed like that made that a lot worse. So I tamped it down to about 70 millivolts, I think, is what I ended up with as a local oscillator pin 6 input signal level, and that seemed to work pretty well. Before I leave this part of the circuit, other implementations, particularly out of experimental methods in RF design book from the ARRL, there is more of a tuned circuit here, so they don't really necessarily use these filters, but there is a tuned circuit here to kind of constrain the bandwidth of the incoming signals. I did not want to have another pot to tweak. I have already several, so I opted to do this method with essentially just series resonant circuits as my bandpass input filters, and that seemed to work pretty well for me. And I don't have to tune anything, so I like that. You know, is it perfect? Probably not. I think I still end up getting some out-of-band stuff that kind of overpowers the chip, but it is pretty decent, I would say, overall. I'm pretty happy with the performance of the radio. So moving over here, this is the NE-602 chip. I'm sorry, not NE-602. This is the LM386 chip. So this is your audio amplifier chip that's paired with the mixer chip. So your inputs from pin 4 and 5 over here come in up here on top, pins 2 and 3. Again, this type of design is really just right out of experimental methods in RF design. I didn't really do anything different for the most part with this LM386. You have a couple 0.01 microfarad capacitors coming in here to pins 2 and 3, and then you've got some kind of high resistances to ground. Pin 4 is grounded. Pin 1, you have this 4.7 microfarad capacitor between pin 1 and 8. Your power supply comes in on pin 6. Again, this is 8 volts from the regulator with a 47 microfarad capacitor to ground. And your headphones are connected, or your audio output, whether you use headphones or amplified speaker, that comes from pin 5 through a 100 microfarad capacitor to the headphones. and then pin 5 is also hooked up to a 10 ohm resistor and 0.01 microfarad capacitor to ground, sort of an RF ground there. Again, I didn't do much experimentation or analysis with this. This is really straight out of experimental method of RF design. I think even the data sheet for the LM386 has pretty much these same values in it. I may say something later, but one of the modifications I think I really want to do on this rig is put in a volume control here. As I said earlier, I'm kind of using the RF gain pot over here. I mean, that's really not a great volume control. So what I'd like to do is sometimes be able to have this opened up, have very little resistance here, have the full signal coming into my circuit, but also be able to turn the volume down. And I'd also like to be able to clean up the audio. I mean, it's really noisy the way it's implemented. I'm not sure if I can do a whole lot with that, but again, that would be something that would help in terms of using this radio for kind of comfortable listening, as opposed to, oh, this is cool, I made this radio, it's fun to play with, but it's kind of a toy, and I don't really use it. Like, if you're going to use this on a regular basis, I think you'd want to kind of improve, put in a volume control and maybe improve the audio a little bit, so it's not quite as, right now there's a lot of high-pitched, kind of squealy, I don't know how to say it, just it's grating on the ear right now a little bit. So that's that for the audio. In terms of the oscillators and the tuning, so the tuning is all done through here, the main tuning, and in conjunction with these oscillator circuits. So for 20, 40, and 80, the oscillators are essentially the same. It's a Colpitts design, so you'll see between base and ground of the transistor, you have these two capacitors, usually pretty close to the same values. Here I've got 180 picofarad for both of them. And I actually experimentally played around with the different bands and these values of these capacitors to sort of maximize signal output and minimize distortion. And I did see some benefit doing that exercise. The circuit's pretty lenient, and seems like you can get away with a lot of different values for these, like the C11, C12. But I did notice some ability to tweak that and get it a little bit stronger output. But again, so these are kind of your biasing resistors. You got 33K between base and collector, 1K between emitter and ground. And you have your 8 volts coming in here and from the switch. So as I change bands, I will turn on or off these different oscillators. So when I'm switched to SW2 is on 20 meters, then I get 8 volts into this circuit. And SW2, where did I put SW2? Just bear with me. Oh, here it is. This is SW2. So that's where that's coming up. I'll talk about that a little bit more in a minute. So the oscillator is kind of the key to my implementation of this circuit. So the action really takes place on this left side over here. So this is what determines both the bandwidth of the band, so how far your tuner tunes, as well as where it tunes. So so this circuit up here, along with this, are all part of that frequency selection process. And because I want to use the same variable capacitors across all 3 bands, I have that switched out, SW3. So this is my main tuning knob, the C7, goes from about 200 to 400 picofarad. This is just a garden variety sort of AM broadcast radio variable capacitor. You can get them on Amazon. That's where I got mine. This is a trimmer capacitor, so it's a variable capacitor, but the plates are a little smaller. It doesn't have as big of a range. I had them in my junk box, so I didn't have to buy one. And this is just a little sort of tweak to adjust the range that this fine tuner does, because I didn't really want it to swing between 12 and 150, so you put that 60, in series with it, and that will constrain the range, make it more of a fine tuner. So that, and this 20 meter VFO comes in here, is where that parallel, this combination of capacitances come into play. So that ends up being in parallel with all these parallel guys, and this series capacitor, and your L7, as well as the capacitors here. So it's a lot of capacitors. I know it's really busy. Could this all be cleaned up? Maybe. What happened is I experimentally determined all these different values to put together in parallel to get me the range that I needed for 20 meters. And what I found through my experimentation is if you were to combine all these values, just say add them up because they're all in parallel, put one giant capacitor there, you don't get the same effect as you do having these individual ones in parallel. So it's kind of tricky, and it's kind of strange. There's parasitics, I guess, at work with these devices, and those all play a part. And it depends on what devices you have on hand and what values you have. So in a practical world, because you can't get exactly, 321.6 picofarad or whatever, you end up combining components in series and in parallel to get the range that you need. And sort of an experimental process. You have to be very careful. These are NP0 capacitors. That's very crucial. If you just get some other type of capacitor, and I've done this, and I did that in this project as well, you end up with this thing drifting really, really badly. I mean, you'll be listening to a station, it'll be going up in frequency, and then it'll go down in frequency. It'll just kind of drift up and down, up and down. Really, really obnoxious. Nobody's going to want to use that. Not even for a fun project radio. It's like that's just not usable. So if you're going to build this and you're new to circuits and whatever, or new to radio building, circuits building, get some NP0 capacitors. You may have to shop around a bit to find them. I don't know how many people these days are building VFOs in this manner, but they are still available, and they're definitely worth it to have in stock if you're going to build this type of a VFO. Really, you're sort of just wasting time if you don't have NP0s because, like I said, the stability is just awful. The stability of these guys is great. The air variable capacitors are wonderful, very stable. I've not had any issue with those. But these ceramics, you got to be careful. This here I used a 8 turns on a T50-2. I don't know how critical the core type is, but this is a core that I had in my junk box that's been used in other HF radio designs, and it seemed to work quite well. And that's pretty much it. So these other circuits, it's going to be 40 meters and 80 meters, really the same scenario. You'll just see the turns goes up as I go down in frequency. You need more inductance, which is probably kind of intuitive to anyone who's dealt with RF much with antennas or circuits. And as it turns out, the number of capacitors I needed in parallel shrunk as I went down in frequency. I think that's just sort of happenstance. I don't know that that really means much. And again, these Colpitts capacitors, these bottom two, change in value as I go down a little bit. So that's pretty much it, really. The only other thing is here I've got the input power circuit. So I have 12 volts coming through, and I use a diode for reverse polarity protection. So I've had a lot of radios that I built. I don't know a lot because I haven't really built a lot. The radios that I've built, I don't always do that. And I've fried some components before and had to replace them. And sometimes it's a pain. It depends on how they're installed. You don't really want to have to desolder chips and stuff like that. So it's a real simple thing to just put in a diode into this circuit. And as you can see here, if you have a negative polarity coming in, this diode will just block it. And you're really unable to conduct any current. So you're good to go. If somehow it blew out diode, that's fine. Diodes are pretty easy to replace. This one's just floating in the air. It's not even tied down to anything, so it'd be really, really easy to desolder it. I don't think it would normally blow it out anyway. This chip is a 78L08, so there's a whole series of these little regulator chips. They look kind of like BJT transistors, little 3-pin devices. They're really pretty handy, and it gives you some voltage stability around 8 volts in this case. That's the 78L08. There's also like an L06, and there's different voltages. But 8 volts seems to work quite well for this particular circuit. And the output, again, goes to a switch port here, or pole, I should say, pole number 2, and that gives you the regulated voltage to the various oscillators in the circuit. Again, here I have voltage out goes to the NE-602, so I don't need to switch the NE-602 or the LM386. They're always going to have voltage applied to them as long as the radio is on, so that's always going to be here. I don't need to go through the switch. The other thing to point out is I have the LCD display coming off of up here, and I believe I took it up here because it needed a little bit more voltage than the 8 volts. So coming after this diode, I've got like 11 volts or so at this node here, and that was better to actually power the LCD display, I believe. I could be wrong on that, but I think that's why I did that. And it seems to work quite well that way. That display is a whole nother conversation. I'm not going to get into that. That was another video I did, but it's made by QRP guys, and it's their frequency counter for QRP kits. It's an excellent, excellent kit. I would highly recommend it if you want to build anything or you just want a frequency counter to have in your shack. That would be a great buy. It was very inexpensive. I mean, it was like $20 or $30 or something. It was crazy. I mean, it was a great, great purchase. In a little circuit like this, it really brings up the kind of professionalism or just, I don't know, ease of use to have that display. So that's going to be about it. All of this is going to be on a blog. I'm going to talk about the radio and about some of the design choices and things and some of the questions that I still have about it. So definitely check that out, and I'll have a link below to the blog. And again, there's another video I'm posting that will kind of show you some of the aesthetical kind of final things that I did. I painted the case red, and I put some lettering on it, and there's little things like that that kind of make it fun, make it your own, which I think is important. And I'll get into that on that other video. This one's gone on pretty long, so I'm going to go ahead and say 73s for now. And thank you so much for watching, and thank you for subscribing.